June 19th, 1918, Pikes Peak, Colorado, 14,109 feet above sea level. Dr. Sanford Alexander Moss stood beside a Liberty V-12 engine mounted on a truck bed, watching his colleagues struggle to breathe in air so thin that even walking felt like climbing stairs. The tiny, spectacled General Electric engineer with his distinctive Van Dyke goatee looked almost comical next to the massive military men surrounding him. They thought he was brilliant. They also thought he was slightly mad. The Army Air Service officers had dragged this 350-horsepower engine up a mountain road to test Moss's claim about a device he called a turbosupercharger. Down at McCook Field in Dayton, this Liberty engine produced 354 horsepower. Up here, in air pressure barely half that at sea level, it managed only 230 horsepower. The aircraft depending on this engine couldn't climb, couldn't fight, couldn't even stay, aloft at altitudes where German fighters operated with impunity. Moss claimed his device could change that. The Army officers were skeptical. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Moss attached his contraption to the Liberty engine, 2 rotors mounted on a single shaft with bearings at either end, a 10-inch diameter turbine wheel spun by exhaust gases, a centrifugal compressor of similar diameter. The concept was elegant in theory, nearly impossible in practice. The turbine had to spin at enormous speeds in temperatures exceeding 1,500 degrees Fahrenheit, while the compressor forced thin mountain air into the engine's intake, tricking the motor into believing it sat at sea level. The test began. The engine roared to life. The turbine screamed. The Liberty engine produced 377 horsepower, more power at 14,000 feet than it generated at sea level. The Army officers stopped laughing. Within 3 years, a Lepaire biplane equipped with Moss's turbosupercharger would set an international altitude record exceeding 40,000 feet, more than double what any naturally aspirated aircraft could achieve. The turbosupercharger would enable high-altitude bombing raids, long-range escort missions, and ultimately help win World War II. But in 1918, standing on that mountain, Moss had proven something fundamental. The laws of physics didn't care about altitude if you had enough engineering audacity. An engine breathing compressed air at 14,000 feet could outperform an engine breathing thin air at sea level. This revelation would echo through aviation development for decades. It would define American fighter design philosophy, and it would terrify German engineers when they finally understood what it meant. 21 years later, in the spring of 1939, another immigrant engineer sat in a meeting room at Wright Field in Dayton, Ohio. His name was Alexander Kartveli, though friends called him Sasha. Born in Tiflis, Georgia, in 1896, Kartveli had fled the Bolsheviks like so many talented engineers of his generation. He'd worked for Blériot in France, where one of his designs had grabbed the world speed record. He'd immigrated to America in 1927, invited by millionaire Charles Levine. By 1939, he was vice president of engineering at Republic Aviation, successor to Alexander de Seversky's aircraft company. The meeting at Wright Field was urgent. Germany had begun its rampage across Europe. Poland would fall within months. France would follow within a year. Britain would stand alone. And American military leaders understood with growing horror that the United States Army Air Corps possessed exactly 0 fighters capable of competing with the Messerschmitt Bf-109 or the soon-to-appear Focke-Wulf 190. Lieutenant Colonel Howard Bogart, Major Franklin Carroll, Captain Marshall Roth, and Major Lawrence Craigie presented specifications for what America would need, not what they hoped to build someday, what they needed immediately. A ceiling of 40,000 feet, maximum true airspeed of at least 400 miles per hour at optimum altitude, no fewer than 6 machine guns with heavy armor protection for the pilot. The specifications violated every principle of fighter design that had governed aviation since the Great War. European fighters emphasized lightweight construction, streamlined efficiency, nimble maneuverability. Every gram was scrutinized, every design choice optimized for performance. The American specifications demanded something entirely different. They demanded an aircraft that could fly higher than any German fighter, faster than most at altitude, and survivable enough to bring pilots home despite taking damage that would obliterate lighter designs. Kartveli listened. Then he took a train back to New York. According to legend, during that overnight journey, he pulled out a sheet of paper and sketched an aircraft that would either revolutionize fighter design or become the most expensive failure in American aviation history. He called it the XP-47B. History would know it as the P-47 Thunderbolt, and its success or failure depended entirely on one component, the same device Sanford Moss had perfected on Pikes Peak 21 years earlier, the exhaust-driven Turbosupercharger. The problem Kartveli faced was brutally simple. Physics demanded trade-offs. You could build a light fighter that climbed quickly and turned tightly at low altitude, or you could build a heavy fighter with sufficient fuel, armor, and weapons to escort bombers deep into Germany. You could not build both. Not with existing technology, not with conventional design approaches. European designers had chosen lightweight performance. The Messerschmitt Bf. 109 weighed 7,500 pounds at combat takeoff weight. The Supermarine Spitfire weighed 9,500 pounds. The new Focke-Wulf 190 weighed 10,800 pounds. Kartveli's initial calculations suggested his fighter would weigh 17,500 pounds at maximum takeoff weight, nearly twice the weight of Germany's most successful fighter. His colleagues thought he was insane. His former boss, Alexander de Seversky, had been forced out of his own company, partly because his aircraft designs were considered too heavy, too expensive, too complex. Now Kartveli proposed building something even larger, a fighter that seemed to violate every lesson learned in 3 years of air combat over Europe. But Kartveli understood something his critics did not. The specifications demanded 40,000-foot ceiling. At 40,000 feet, air pressure is approximately 20% of sea level pressure. A naturally aspirated engine produces approximately 20% of its rated power. A lightweight fighter might climb to 40,000 feet. It couldn't fight there. It had barely enough power to maintain level flight. It certainly couldn't maneuver, couldn't chase enemy aircraft, couldn't protect bombers, unless the engine could breathe compressed air. Unless the fighter incorporated a turbo-supercharger capable of maintaining sea-level manifold pressure at 40,000 feet. And that's where Kartveli's radical design philosophy emerged. He would build the airplane around the turbocharger, not add a turbocharger to an existing airframe, not compromise the system to save weight. He would design the optimal turbo-supercharger installation first, then construct the entire aircraft around it. This had never been attempted before. Previous attempts at turbo-supercharging fighter engines had failed because designers tried to retrofit the systems into existing airframes. The results were invariably disappointing. Poor ducting reduced efficiency. Inadequate cooling caused failures. Vibration destroyed components. Complex control systems confused pilots. Kartveli rejected this approach entirely. His turbo-supercharger would be integral to the design from the first pencil stroke. The General Electric turbo-supercharger itself was a remarkable device. A turbine wheel approximately 9 inches in diameter sat in the bottom of the fuselage, roughly halfway between cockpit and tail. Engine exhaust gases were routed through pipes running along each side of the cockpit to drive this turbine at speeds exceeding 21,000 revolutions per minute. At full power, these pipes glowed cherry red. The spinning turbine drove a centrifugal compressor that forced air into an intercooler system, cooling the compressed air before it entered the engine. This allowed the Pratt & Whitney R2800 double WASP 18-cylinder radial engine to maintain high manifold pressure at altitudes where German fighters gasped for air. But the engineering challenges were extraordinary. The ducting alone represented a masterpiece of aerodynamic design. Exhaust gases had to flow from 18 cylinders arranged in 2 rows, merge into 2 main pipes, travel the length of the fuselage without excessive heat loss, drive the turbine with maximum efficiency, then exit through a wastegate system that regulated boost pressure. The intake system was equally complex. Air entered through the distinctive horse-collar-shaped opening at the front of the cowling, passed through oil coolers, flowed to the intercooler after compression by the turbocharger, then finally entered the engine's induction system. Every inch of ducting affected performance. The size implications were unavoidable. The turbosupercharger and its associated ducting demanded a deep fuselage. The deep fuselage required mounting the wings in a relatively high position. The high wing position necessitated extremely long landing gear, struts to provide ground clearance for the enormous four-bladed Curtiss electric propeller. 13 feet in diameter, larger than the propellers on many twin-engine bombers. The landing gear itself became an engineering triumph, strong enough to absorb the punishment of carrier-like landings by young pilots, yet able to retract inward into the wings. Kartveli famously told skeptics, "It will be a dinosaur, but it will be a dinosaur with good proportions." He knew what he was building, a massive, heavy, complex fighter that would horrify engineers trained in European traditions of lightweight efficiency. But he also understood the mission. American bombers would fly deep into Germany at 25,000 to 28,000 feet. Their fighter escorts needed to operate comfortably 12,000 to 15,000 feet above them, maintaining energy advantage over any German interceptor. The P-47 could do that. Nothing else could. The XP-47B prototype first flew on May 6, 1941, with test pilot Lowry Brabham at the controls. The aircraft proved impressive immediately. It was fast, achieving 412 miles per hour at 25,800 feet. It climbed well, reaching 15,000 feet in 5 minutes, and it maintained performance at altitudes where other fighters struggled. But the true revelation came during high-altitude testing. At 30,000 feet, the P-47 maintained 433 miles per hour. The Messerschmitt Bf 109G6 managed approximately 380 miles per hour at similar altitude. The Focke-Wulf 190A series began experiencing severe performance degradation above 20,000 feet. German designers had assumed high-altitude combat would be rare. Their fighters were optimized for low to medium altitude performance, where most Eastern Front combat occurred. They featured superchargers designed to provide peak power at specific altitudes, typically 18,000 to 20,000 feet. Above those altitudes, power dropped rapidly. The Germans accepted this trade-off because it simplified design, reduced weight, and improved low-altitude performance where they expected to fight. The P-47 made no such compromises. Its turbosupercharger was a continuously variable system, automatically adjusting boost pressure to maintain optimal engine power from sea level to beyond 40,000 feet, while German pilots had to carefully manage their supercharger gear changes, often experiencing violent transitions that could throw an aircraft into a spin. American pilots simply advanced the throttle. The turbo-supercharger control system handled everything automatically. This represented a fundamental philosophical difference. German engineering emphasized pilot skill, aircraft efficiency, and peak performance at tactically relevant altitudes. American engineering emphasized technological solutions, automated systems, and broad performance across all altitudes. Neither approach was inherently superior, but in the strategic bombing campaign that would define the air war over Europe, altitude performance would prove decisive. By early 1943, P-47 Thunderbolts began arriving in England. The 56th Fighter Group, commanded by Hub Zemke, would become the first unit to take the massive fighters into combat. The pilots were initially skeptical. Coming from P-40 Warhawks or P-39 Airacobras, they found the Thunderbolt intimidatingly large. The cockpit was enormous compared to previous fighters. The aircraft weighed as much as some medium bombers. Ground crews joked that you didn't climb into a P-47, you climbed aboard it. But as pilots gained experience, skepticism transformed into confidence. The Thunderbolt flew like a much smaller aircraft once airborne. Controls were well harmonized. Visibility from the bubble canopy was exceptional. And most importantly, performance at altitude matched the test reports. The P-47 could climb to 30,000 feet and fight effectively. It could dive away from any German fighter, and it could absorb battle damage that would destroy lighter aircraft. The first major engagements occurred in spring 1943, as P-47s began escorting B-17 and B-24 bombers on raids into occupied France and the Low Countries. German fighter pilots, accustomed to facing Spitfires and the occasional P-38 Lightning, encountered this new American fighter with a mixture of curiosity and contempt. Intelligence reports described the P-47 as large and cumbersome. Surely it would be easy prey for nimble Messerschmitts and Focke-Wulfs. The reality proved far different. At 25,000 feet and above, the P-47 dominated. German pilots attempting climbing attacks found the American fighters maintaining altitude advantage effortlessly. Diving attacks that worked against Spitfires failed against Thunderbolts that simply dove faster. And any German pilot who made the mistake of engaging in extended combat at high altitude discovered his engine losing power while the American fighter maintained full performance. Major Gerhard Barkhorn, second highest scoring ace in history with 301 victories all on the Eastern Front, would later describe the difference. In the East, if you had altitude and speed advantage, you controlled the engagement. You attacked, destroyed the enemy, then climbed away. In the West, the Americans had altitude and speed advantage. They decided when to engage. You couldn't climb above them. You couldn't dive away from them. And if you tried to fight at their altitude, your engine suffocated while theirs sang with full power. The Turbosupercharger created this advantage. While German pilots struggled with engines producing 60% of rated power at 30,000 feet, American pilots enjoyed engines delivering near full power at the same altitude. This transformed aerial combat. Energy fighting, the hallmark of German tactics, required the ability to convert altitude to speed, and speed back to altitude. The P-47 could do both better than any German fighter at tactically relevant altitudes. German fighter commanders quickly recognized they faced a fundamental problem. Their entire tactical doctrine assumed German fighters would possess performance superiority, allowing slashing attacks followed by escape maneuvers. Against the P-47, this doctrine failed. The Thunderbolt absorbed the initial attack, then pursued. In extended combat, the P-47's advantages became overwhelming. It could maintain energy, it could fight at altitudes where German aircraft struggled, and it refused to die despite damage that should have been catastrophic. By summer 1943, Luftwaffe tactical directives began reflecting this new reality. Fighter wings issued instructions emphasizing the need to achieve kills on the first attack pass. Pilots were warned not to assume visible strikes meant the aircraft was finished. Most critically, they were told not to remain in extended combat with P-47s at high altitude. The admission was implicit but clear. German pilots flying aircraft they believed superior were being instructed to avoid sustained combat with American fighters. The psychological impact was profound. German fighter pilots had begun the war with absolute confidence. Their aircraft were faster than Polish fighters, more maneuverable than French fighters, better armed than British fighters initially encountered. They had dominated the skies through superior performance and superior tactics. Now they faced an enemy who seemed indifferent to their best attacks, who could choose when and where to engage, and who operated at altitudes where Luftwaffe fighters barely functioned. What German pilots didn't fully understand yet was that the P-47's high-altitude dominance was not an accident of design. It was the design. Alexander Kartveli had built an aircraft specifically to excel where American bombers operated. He had accepted weight penalties, manufacturing complexity, and low-altitude performance compromises to create an aircraft that could escort B-17s and B-24s all the way to their targets. The Turbosupercharger made it possible. Without that single component, the P-47 would have been just another heavy fighter with mediocre performance. With it, the Thunderbolt redefined what fighter escorts could accomplish. The German aviation industry watched these developments with growing concern. Captured intelligence reports described the turbosupercharger system. Messerschmitt and Focke-Wulf engineers studied what little information they could obtain. They recognized immediately that matching the P-47's altitude performance would require developing similar exhaust-driven turbo-supercharging systems. But developing such systems required time, resources, and industrial capacity that Germany increasingly lacked. The BMW 801 radial powering the Fw-190 190 featured a sophisticated two-stage mechanical supercharger. It was a brilliant piece of engineering that provided good performance from sea level to approximately 20,000 feet. Above that altitude, performance degraded rapidly. Adding an exhaust-driven turbocharger to the BMW 801 would require extensive redesign of the engine, development of ducting systems, creation of intercoolers, and testing under combat conditions. It would take years. The Messerschmitt Bf 109 faced similar limitations. Its Daimler-Benz liquid-cooled inline engine used mechanical supercharging with gear-driven stages. Retrofitting a turbo-supercharger would require complete fuselage redesign. The 109's compact, lightweight construction left no room for the extensive ducting the turbocharger demanded. Creating a turbo-supercharged 109 meant designing an entirely new aircraft. German aviation officials authorized multiple programs attempting to address the high-altitude problem. The Focke-Wulf 190B and C variants experimented with turbo-supercharging but encountered endless development problems. Engine fires destroyed prototypes, turbine wheels failed regularly, control systems proved unreliable. By the time engineers solved these problems, the war situation had deteriorated so badly that production resources had to focus on existing designs rather than experimental systems. The Focke-Wulf 190D series, powered by the Junkers Jumo 213 liquid-cooled inline engine, represented Germany's best response. The Dora, as pilots called it, featured improved altitude performance through mechanical supercharging and water methanol injection. It achieved impressive results, reaching 39,000 feet service ceiling with performance remaining competitive up to approximately 20,000 feet. Above that altitude, the Dora gradually suffered. The aircraft could reach high altitudes. It couldn't fight effectively there. The Ta-152, developed by Kurt Tank as the ultimate high-altitude interceptor, came closest to matching the P-47's capabilities. With its long wingspan, powerful engine, and sophisticated supercharging, the Ta-152 could exceed 45,000 feet with respectable performance. Only 43 were built before war's end. Far too few to affect the strategic situation. Too late to matter. Meanwhile, American production delivered P-47s in numbers that stunned German intelligence. Republic Aviation's Farmingdale facility produced approximately 60 aircraft monthly by mid-1944. Curtiss Wright's Buffalo facility added another 55 per month. Combined production exceeded 115 fighters, monthly from just 2 factories building a single type. Total American fighter production in 1944 exceeded 38,000 aircraft. Germany managed approximately 25,000 fighters the same year, despite mobilizing every resource available. The turbo-supercharger's impact extended beyond performance advantages. It created strategic possibilities German fighters couldn't counter. American bomber formations could operate at altitudes where German interceptors struggled. P-47 escorts could maintain position above bomber streams, forcing German fighters to attack from below where they were vulnerable. And the escorts could pursue German fighters through altitude ranges where Luftwaffe aircraft lost power, while American fighters maintained full performance. The mathematics of attrition became increasingly unfavorable for Germany. Even if German pilots achieved favorable kill ratios through perfect tactics, American production replaced losses within days. German losses were barely replaceable. Experienced pilots killed in action could not be replaced at all. Training time had shrunk from over 200 hours in 1942 to barely 50 hours by late 1944. New German pilots arrived at frontline units with minimal experience facing American opponents with 5 times more training flying superior aircraft in greater numbers. The strategic bombing campaign that devastated German industry was enabled by fighter escorts. The P-47, along with the P-51 Mustang and P-38 Lightning, made strategic bombing viable by winning air superiority over Germany itself. The Turbosupercharger was central to this achievement. It provided the altitude performance necessary to protect bombers at their operating heights, while maintaining energy advantage over German interceptors. The autumn of 1943 brought the strategic bombing campaign to full intensity. American heavy bombers struck deep into German industrial heartland, targeting ball-bearing plants at Schweinfurt, aircraft factories at Regensburg, synthetic oil refineries across the Ruhr Valley. The losses were staggering. On October 14, 1943, a force of 291 B-17s attacked Schweinfurt. 60 bombers were shot down. 17 more were damaged beyond repair. 600 crewmen were killed or captured. The mission became known as Black Thursday. The problem was range. P-47 Thunderbolts could escort bombers to the German border, occasionally deeper when equipped with external drop tanks. But beyond approximately 300 miles from English bases, the bombers flew unescorted. German fighter commanders concentrated their forces at those points where American escorts had to turn back. They attacked in formation, sometimes massing over 100 fighters against a single bomber stream. The results were catastrophic. But even during these desperate months, German pilots noticed something troubling about the brief engagements they had with P-47 escorts. The American fighters were nearly impossible to shoot down. Combat reports from German units described hitting Thunderbolts repeatedly, seeing strikes on wings and fuselage, watching pieces fly off, yet the aircraft continued flying. Some German pilots expended their entire ammunition load on a single P-47 without achieving a kill. Major Heinz Baer, third highest scoring German ace with 220 victories, flew against American bombers in the West during this period. He described his experience in post-war interviews. We learned to fear the P-47 specifically. Not because it was the fastest fighter, the Mustang was faster at most altitudes. Not because it was the most maneuverable, the Spitfire could turn inside it. We feared it because it represented something we couldn't match. American industrial philosophy made tangible. They built aircraft, assuming they would be damaged in combat, then engineered them to survive anyway. The Turbosupercharger system itself demonstrated this philosophy. German engineers examining intelligence reports on the P-47's power plant were astounded by the redundancy built into every component. The exhaust ducting used heavy-gauge steel that added weight but prevented ruptures. The turbine housing was over-engineered to prevent failures even when operating at extreme temperatures. The intercooler system featured multiple passages so that damage to one section didn't compromise the entire system. The wastegate controls had manual backup in case automatic systems failed. Every design choice prioritized reliability over minimum weight. A German engineer would have looked at the P-47's turbosupercharger installation and found dozens of places to save weight through more efficient design. An American engineer looked at the same installation and saw a system that would keep functioning, despite battle damage, temperature extremes, and rough handling by pilots with minimal training. This fundamental difference in design philosophy extended throughout the aircraft. The airframe used thicker gauge aluminum than comparable German fighters. Structural load paths were redundant, so failure of one spar didn't cause catastrophic collapse. The massive radial engine provided a protective shield in front of the pilot, while its distributed cylinder arrangement meant losing several cylinders to enemy fire still left enough power to reach friendly territory. Self-sealing fuel tanks were not just rubber bladders, but sophisticated multi-layer systems that could seal multiple punctures. Armor protection surrounded the pilot from every angle with face-hardened steel capable of stopping 20mm cannon rounds. German pilots, accustomed to aircraft where armor was minimal to save weight, faced opponents who sat in what American ground crews called an armored bathtub. The seatback was hardened steel armor. The headrest contained additional plating. Beneath the seat, another armor plate protected from ground fire. In front, thick bulletproof glass windscreen could stop 30mm cannon shells. The Americans had built a fighter around the assumption that it would be shot at and needed to protect the pilot anyway. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By spring 1944, German aviation intelligence had compiled extensive reports on the P-47 based on combat encounters, interrogation of captured pilots, and examination of wrecked aircraft. The conclusions were sobering. The Thunderbolt represented American engineering philosophy applied without the resource constraints German designers faced. It was heavy, complex, expensive to manufacture, and required sophisticated systems throughout. Yet it worked brilliantly for its intended purpose. The turbosupercharger specifically drew German engineering attention. Luftwaffe technical reports acknowledged that matching the P-47's high-altitude performance would require developing similar exhaust-driven supercharging systems. But the reports also noted that even if Germany successfully developed such systems, implementing them would require years of development time, massive industrial resources, and manufacturing capacity that simply didn't exist in 1944. The BMW Engine Works had attempted turbo-supercharging the 801 radial as early as 1941. The project encountered insurmountable problems. Turbine blades failed at operating temperatures. Ducting proved difficult to route within the Fw-190s compact fuselage. Control systems were unreliable. Intercooler efficiency was inadequate. By 1943, BMW had abandoned the effort as requiring too many resources with insufficient probability of success. Daimler-Benz experimented with turbo-supercharging the DB603 engine intended for high-altitude Messerschmitt variants. The results were similarly disappointing. The liquid-cooled inline engine's configuration made ducting even more challenging than with radials. Heat management proved nearly impossible. The project consumed engineering resources desperately needed for other development efforts while delivering no operational aircraft. The fundamental problem was that turbo-supercharger development required infrastructure, experience, and institutional knowledge that only General Electric possessed. Dr. Sanford Moss and his team at GE's Lynn Works had spent decades perfecting the technology. They understood the metallurgy required for turbine wheels spinning at 20,000 revolutions per minute in 1500-degree exhaust gases. They knew how to design diffusers that efficiently converted velocity into pressure. They had solved the bearing problems that destroyed early turbo-superchargers. They had created wastegate control systems that regulated boost pressure automatically. This knowledge couldn't be replicated quickly. German engineers could examine captured turbo-superchargers, which they did when opportunities arose. They could measure dimensions, analyze materials, study construction techniques, but understanding how something worked and being able to manufacture it reliably under combat conditions were entirely different challenges. Even if Germany had successfully copied the GE turbo-supercharger, producing it in quantity would have required retooling factories, training workers, establishing quality control procedures, and debugging countless manufacturing problems. The timeline stretched to years. Germany didn't have years. Meanwhile, the P-47 force in Europe grew steadily. By D-Day, June 6, 1944, multiple fighter groups flew Thunderbolts in both bomber escort and ground attack roles. The aircraft's versatility demonstrated another advantage of Kartvel's overbuilt philosophy. A fighter designed with sufficient structural strength to survive high-altitude combat could also withstand the stresses of low-altitude ground attack missions. The P-47 could carry 2,000 pounds of bombs or 10 rockets in addition to its 850 caliber machine guns. The combination of armor protection, powerful armament, and rugged radial engine made it extraordinarily effective against ground targets. German ground forces learned to dread the distinctive sound of the R-2800 engine. They called P-47s Jabos, short for jagged bomber or fighter bomber, but the term carried fear rather than simple description. The Turbosupercharger's contribution to ground attack capability was indirect but significant. Because the P-47 excelled at high-altitude escort, American commanders could assign it to ground attack missions, knowing bomber escort capacity remained adequate with other fighter types. The Thunderbolt's altitude performance freed it for missions where that performance wasn't required, but its toughness was essential. Throughout the summer of 1944, P-47 groups flew thousands of ground attack sorties, supporting the Allied advance from Normandy. They destroyed German armor, attempting to counterattack. They demolished supply columns. They attacked railway infrastructure. The scale was unprecedented. Pilots claimed destruction of tens of thousands of railway cars, locomotives, armored vehicles, and trucks. These claims were certainly inflated, as all aerial combat claims are, but even conservative assessments suggested the P-47's ground attack campaign significantly disrupted German logistics. The aircraft's survivability proved as crucial in ground attack as in air-to-air combat. German anti-aircraft defenses, equipped with 20mm, 37mm, and 88mm guns, discovered that bringing down a P-47 required far more hits than any other Allied aircraft. Standard doctrine assumed 2 or 3 20mm hits would destroy a fighter. Against the P-47, crews reported needing 10 or more direct hits, and even then the aircraft often made it back to Allied territory. The radial engine was particularly difficult to stop. Unlike inline engines, where a single cooling system hit caused rapid failure, the R-2800 could lose entire cylinders and continue running. American pilots reported flying home on engines missing 3 or 4 cylinders, still producing enough power to maintain altitude. One pilot returned to base with 7 of 18 cylinders destroyed by flak. The engine ran rough, trailing smoke, but it ran. The pilot made a successful landing. The Turbosupercharger system's robust design contributed to this survivability. Even when battle damage severed exhaust ducting or damaged the turbine, the engine could operate without turbocharger boost at reduced power. The system was designed to fail gracefully rather than catastrophically. A P-47 with turbocharger damage became a heavy fighter with mediocre high-altitude performance, but it could still fly, still fight at lower altitudes, and most importantly, still bring the pilot home. German fighter pilots interviewed after the war consistently described the frustration of engaging P-47s. Oberst Johannes Steinhoff, 176 Victory Ace who survived being shot down multiple times, provided an eloquent summary in his memoir. We learned to respect all our opponents, the Russian pilots for their courage, the British for their determination, the Americans for their numbers. But we feared the P-47 specifically because it represented American industrial might in tangible form. We flew graceful, efficient, deadly machines. They flew armoured fortresses, and their fortresses defeated our thoroughbreds. The technical data supported these impressions. Post-war analysis by the United States Strategic Bombing Survey examined thousands of combat reports and damage assessments. Their findings quantified what German pilots experienced firsthand. The P-47 consistently required far more hits to bring down than other Allied fighters. German pilots expended more ammunition per P-47 destroyed than for any other Allied fighter type. This ammunition expenditure had strategic implications. German fighters carried limited ammunition. A Messerschmitt Bf-109 G6 typically carried 200 rounds per 20mm cannon and 1,000 rounds per machine gun. A Focke-Wulf 190A8 carried similar loads. A single combat sortie might encounter multiple American fighters. Expending most or all ammunition on one P-47 left German pilots defenseless against others. Entire fighter formations were being rendered combat ineffective not by being shot down, but by being forced to waste ammunition on unkillable American escorts. General Lieutenant Adolf Galland, commander of all German fighter forces, attempted to address this problem through tactical directives. In October 1943, he ordered pilots to ignore American fighters and focus exclusively on bombers. The theory was that bombers were the real threat. Fighters were just escorts. Destroying the bombers would end the strategic bombing campaign. The directive failed catastrophically. American fighter pilots, freed from defensive concerns by their aircraft's survivability, became even more aggressive. They would dive on German formations attempting to attack bombers. They would fly through initial defensive fire that might damage but not destroy their aircraft. Then they would systematically destroy German fighters with massed 50 caliber fire at close range. The P-47s' 8 machine guns, while individually less powerful than German 20mm or 30mm cannons, fired at a combined rate of 1,200 rounds per minute. More importantly, the American machine guns were extraordinarily reliable, rarely jamming even in extended combat. German cannons frequently malfunctioned. The MG-151 20mm cannon was generally reliable, but the larger Mk-108 30mm cannon suffered regular stoppages. German pilots described the frustration of lining up perfect shots only to have their main armament fail at the critical moment. Meanwhile, American pilots could hold the trigger for extended bursts, knowing all 8 guns would continue firing. The summer of 1944 brought another revelation about the P-47's capabilities. With improved external fuel tanks, the Thunderbolt's range extended to the point where it could escort bombers to targets deep in Germany. The P-51 Mustang possessed longer range and was better suited for extreme distance missions. But the P-47 could now reach most German targets, and its survivability made it preferred for the most dangerous missions. Initial penetration of German airspace often fell to Thunderbolt groups. Their armor and structural strength allowed them to absorb the heaviest defensive fire as they led bomber streams into German territory. Combat over heavily defended targets like Berlin, Munich, or Vienna saw P-47s operating in environments where lighter fighters would have suffered unacceptable losses. The Thunderbolts took damage, sometimes severe damage, but they kept fighting and brought pilots home. The Turbosupercharger's contribution to these missions was maintaining combat capability at 25,000 to 30,000 feet where bombers operated. German interceptors had to climb to reach the bombers. P-47 escorts already held altitude advantage. When German fighters attempted climbing attacks, they fought with engines producing 70% power, while American engines maintained near full power. The energy disadvantage was crippling. One particularly revealing engagement occurred over Brunswick in January 1944. A force of Messerschmitt Bf 109 G6s from Jagdgeschwader 3 attempted to intercept a bomber formation at 28,000 feet, escorted by P-47s from the 56th Fighter Group. The German fighters climbed to attack position, then discovered their engines losing power as altitude increased. The Messerschmitts could barely accelerate. Turns bled energy they couldn't recover. Meanwhile, the Thunderbolts maneuvered aggressively, maintaining speed and altitude advantage throughout the engagement. The German formation leader broke off the attack after losing 3 aircraft without inflicting any damage on the bombers. His after-action report noted that at 28,000 feet, his fighters lacked sufficient power to engage effectively. He requested permission to attack only bomber formations below 20,000 feet. The request was denied. Bombers didn't fly below 20,000 feet over Germany. They couldn't. German flak defenses were too deadly at lower altitudes. The bombers had to fly high, the escorts flew higher, and the Turbosupercharger made that possible. By autumn 1944, the air war over Germany had shifted decisively in favor of Allied forces. American fighter production had overwhelmed German defensive capacity. Experienced Luftwaffe pilots were being killed faster than they could be replaced. Fuel shortages limited training and operational flying, and the psychological advantage had reversed completely. German pilots who had begun the war with absolute confidence now flew knowing they faced numerically superior enemies in qualitatively superior aircraft. The P-47's reputation among German pilots had evolved from curiosity to concern to outright fear. Stories circulated about Thunderbolts that should have been destroyed, but kept flying. Every fighter group had tales of hitting P-47s with cannon fire that would obliterate a Messerschmitt, watching the American fighter smoke and shudder, then watching it turn around and shoot down the attacker. The psychological impact was devastating. German tactical evolution reflected this reality. Fighter units developed specific procedures for engaging thunderbolts. Attack from maximum altitude advantage if possible. Make a single high-speed pass. Do not remain in combat if the P-47 survives the initial attack. Do not attempt to dive away. The Thunderbolt dives faster. Do not attempt climbing combat above 20,000 feet. The Thunderbolt maintains power at altitude. These procedures, when followed, sometimes resulted in successful engagements, but they represented a fundamental admission of inferiority. The Luftwaffe's best pilots, flying aircraft they had once believed superior, were being instructed to avoid sustained combat with American fighters. Meanwhile, American pilots flew with increasing confidence. They knew their aircraft could absorb punishment. They knew the turbosupercharger gave them altitude advantage. They knew German fighters couldn't escape by diving or outclimb them at high altitude. This confidence translated into aggressive tactics that maximized the P-47's strengths. The final months of 1944 brought Operation Bodenplatte, Germany's last major offensive air operation in the West. On January 1, 1945, over 850 Luftwaffe fighters launched coordinated strikes against Allied airfields in Belgium and Holland. The operation achieved initial surprise, destroying 305 Allied aircraft on the ground and damaging another 190. But as Allied fighters scrambled and engaged, the results became catastrophic for Germany. The battle lasted most of the day. By evening, the Luftwaffe had lost 271 aircraft, destroyed with 143 pilots killed or missing. The losses included 3 Geschwader Commodore, 5 Gruppenkommandeur, and 14 Staffelkapitani. The loss of experienced leadership was irreplaceable. More significantly, the operation had expended fuel and aircraft that Germany could not replace, for gains that were tactical at best. P-47 groups engaged throughout Bodenplatte. The Thunderbolts lost aircraft primarily to ground fire during initial German strafing attacks. Not one P-47 was lost in air-to-air combat, despite being outnumbered in many engagements. German pilots returning from Bodenplatte reported the same frustrating experience they had suffered throughout the war. They would hit P-47s repeatedly, see visible damage, yet watch the American fighters continue fighting. The turbosupercharger's contribution to these victories was indirect but real. Because P-47 pilots knew their aircraft could survive damage, they suppressed attacks that pilots in more fragile aircraft would have broken off. This aggressiveness, enabled by engineering rather than just courage, proved decisive. The war ended in May 1945. The final accounting showed the P-47's extraordinary success. Over 15,683 Thunderbolts were built during the war. They flew 546,000 combat sorties in the European and Mediterranean theatres. They were credited with destroying 3,752 enemy aircraft in air-to-air combat, plus approximately 3,000 more on the ground. But the most important statistic was loss rate, 0.7% per sortie in the European theatre. For every 1,000 sorties flown, only 7 P-47s were lost. By comparison, the P-38 Lightning lost 13 per 1,000 sorties. The P-51 Mustang lost 9 per 1,000. The P-47's survivability translated directly into pilot survival. Of American aviators who served in Europe, those flying P-47s had the highest survival rate of any fighter pilots. This wasn't statistical anomaly. It represented thousands of young men who came home to their families instead of dying over Germany. The engineering decisions that made the P-47 tough were humanitarian decisions, though Alexander Kartveli probably never framed them that way. He built an aircraft designed to bring pilots home. The turbosupercharger gave it altitude performance. The armor protected the pilot. The structural strength absorbed battle damage. The redundant systems kept functioning when primary systems failed. Every design choice prioritized survival over elegance. And survival won. German aces interviewed after the war uniformly expressed respect bordering on awe for the Thunderbolt's toughness. When aviation historians asked General Lieutenant Adolf Galland what Allied aircraft he most respected, His answer was immediate: the P-47 Thunderbolt. Not because it was the best fighter aerodynamically. The P-51 was faster and more maneuverable. The Spitfire was more elegant, but the Thunderbolt was nearly unkillable. You could hit it and hit it and hit it, and it would keep coming. That was psychological defeat, knowing that your best shots might not be enough. The Turbosupercharger made the psychological victory possible. It gave American fighters altitude advantage that German pilots couldn't overcome. It enabled bomber escort missions at heights where Luftwaffe interceptors struggled. It represented engineering sophistication that Germany recognized but couldn't match given wartime resource constraints. And it embodied American industrial philosophy: build systems that work reliably despite damage, operator error, or extreme conditions. Accept weight penalties and manufacturing complexity to achieve robust performance. Dr. Sanford Moss died in November 1946 at age 74. He had lived to see his turbosupercharger become decisive military technology. The high-altitude bombers that devastated German industry were enabled by his invention. The fighter escorts that protected those bombers dominated through altitude performance his turbosupercharger provided. He had received the Collier Trophy in 1941. He had been celebrated as a genius, but he remained the same slightly odd engineer who carried quarters to prove probability laws and refused to fly in the aircraft that used his technology. Alexander Kartveli continued designing aircraft after the war. He led development of the F-84 Thunderjet, the F-84F Thunderstreak, and the Fw-190s Thunderchief. He was heavily involved with the A-10 Thunderbolt II, which carried forward his philosophy of building survivable aircraft that brought pilots home. He died in 1974, having witnessed American aviation dominance built partly on principles he had established with the P-47. The legacy of the turbosupercharger extended far beyond World War II. Post-war fighter development initially moved toward jet engines, which used similar turbocharger principles in their turbine sections. The knowledge gained developing turbosuperchargers influenced jet engine design directly. General Electric's turbosupercharger experience positioned the company to develop America's first operational jet engines. The institutional knowledge transferred seamlessly. The P-47 influenced fighter design philosophy globally. American fighters continued prioritizing survivability alongside performance. Soviet designers, capturing German analysis of the P-47 and conducting their own studies, shifted toward emphasizing protection more than pre-war designs had. The global evolution of fighter design moved toward the American model, away from the German model of performance over protection. The specific lesson of the turbosupercharger was that technological solutions could overcome tactical disadvantages. German fighters were more maneuverable at low altitude. The P-47 didn't try to outturn them. It climbed above them where its turbosupercharger provided performance advantage. German fighters could accelerate quickly in level flight at medium altitude. The P-47 didn't chase them there. It dove from above where its weight and structural strength allowed speeds German fighters couldn't match. Every limitation was countered by leveraging strengths elsewhere. The turbosupercharger was central to this approach. It gave the P-47 a domain, high altitude, where it dominated absolutely. From that domain, it could control engagements, protect bombers, and ultimately win the air war through strategic attrition rather than tactical brilliance. The story of the P-47 Thunderbolt is ultimately the story of engineering philosophy applied to warfare. Alexander Kartveli built an aircraft around a single component, the turbosupercharger, and accepted every compromise necessary to make that component work optimally. The result was an aircraft that seemed wrong by every traditional measure: too heavy, too complex, too expensive. Yet it proved devastatingly effective for its intended mission. It flew higher than German fighters. It escorted bombers deep into Germany. It absorbed battle damage that destroyed other aircraft. It brought pilots home, and it helped win the war. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.